All right, good morning and good afternoon, everyone. Welcome to Beyond Compliance. My name is Aaron Bolshaw here with SafetyChain Software. I'm the moderator of Beyond Compliance. For those of you possibly joining for the first time, it's a periodic industry update for process manufacturers. The goal really to bring you insights around the market that shape the way we grow our business, deliver quality products to customers, mitigate supply chain risk, safeguard our brands, all of this, while of course improving yields and maximizing productivity, which is very, very important. So today, we're getting into the SPC Fundamentals. We have a great guest with us, Michael Parent. Very quickly, the show is brought to you by SafetyChain, which is the #1 plant management platform uniting compliance, safety, quality, and production. But enough about that. That's enough. We use GoToWebinar, as you can tell, which means we've got everyone muted. We can't hear you, but we do want to hear from you. So if you have questions, I'd ask you to use the panel to the right of your screen, should be to the right of your screen, the question panel. Text us some questions through the presentation if you have some thoughtful questions. We're going to get to those at the end. We'll save some time to get to those questions because I'm sure there's going to be some of you that have maybe some specific use cases for maybe your facilities, and we're going to be wanting to hear from you. So with that, I want you to meet Michael Parent. He's a Lean and Six Sigma Master Black Belt and principal of Michael Parent Consulting Services. A very deep experience and background in industrial and operations. The University of Michigan, which is where he's hailing from today, and then got his MBA from William & Mary in Williamsburg, Virginia. He was named a 40 under 40 rising star by the American Society for Quality, which is fantastic. I tried to do that on my career, but I could not do that, so congratulations. And he is also the author of the Lean Innovation Cycle, a multidisciplinary framework for designing value with lean and human-centered design. So very happy to have you with us. Welcome, Michael.
Hi, Aaron. Thanks for having me. And I love that you said I'm hailing from the University of Michigan.
Now,
we do hail to the victors a lot.
Yes, I know. To be fair, I'm a diehard Nebraska Cornhusker fan. So we'll just leave our differences aside while we get into the fundamentals of SPC, shall we?
Sounds good.
So, hey, listen, why don't you take us through to start us off what we're looking to accomplish here with our time. Everyone's time is very valuable. And then I've got a poll question I wanted to start with right after you kind of go through what we're doing here today, okay?
Yeah, sure. So, kind of the topic here is getting to the fundamentals of statistical process control. So what we want to do is first kind of define what statistical process control is. And then we're going to look mainly at two applications of it. The first one is looking at process capability. And then the second ones are really going to look at control charts, and in particular, looking at different types of signals we can pull from control charts, and even doing some kind of diagnostic, analysis, root cause analysis, to really get into, well, if I'm getting these type of signals, how do I improve my process to improve effectiveness, improve yield, and reduce defects? So that's kind of what's on the agenda for us.
Yeah, I love that you're getting to that. Hey, what do you do with it? Right, because there's a lot of parts that a lot of manufacturers kind of get to the bulk of, hey, we got the data, we can visualize it. Then what do you do with it? So I'm really happy that we're going to get the real, hey, what do you do with this? But I want to know first off, right away, I'm going to ask a question. It's a poll question. So in a moment, everyone on the line with us will see a poll come up in front of you. When that happens, just be honest. We're not taking your name. We're not going to show anybody's names. We just want to get an input from you to see what the maturity level of everyone's use of SPC is right now. So is it fully manual, where you're taking manual data and reporting it manually, right? Like if that's an Excel spreadsheet or whatnot. Is it partially automated, so where it means you've got more manual entry and reporting than not? You've got maybe some machine data, but you're still collecting data on paper somewhere. Is it partially manual, where it's more automated and there's less data entry and manual data entry and reporting? Or do you have like the Cadillac? Do you have real-time automated SPC charts that run on live data from your machines? We've got about 40% voted so far. Or, we're always looking for those people that are open and transparent and say, hey, we're looking for a solution. That's why we're here, maybe to listen with Michael as he goes through this. So I got about 60% voted. Last couple of seconds, and I'll close the poll. We'll share the results, and I'm curious on what you're seeing here, Michael. Anything stand out to you?
I thought the one that came up as the majority, I thought that would be what we would see, maybe even higher than 35%. It's good that 7% is real-time automated. That's, you're talking about enterprise alignment to get that done. So you would expect that to be less of the population, but it's really good to see that it's, 7% actually.
Yeah, and that really does unlock some really cool stuff, way beyond sort of what you normally use SPC for. When you're able to tell your operations folks, hey, something's happening over here on your line because of this, and you can adjust it while it's still running, boy, that makes it a pretty powerful weapon. So, all right, well, let's get back into it then. Let's get going. Michael, why don't you take us through, just the fundamentals, SPC.
Yeah, so at a high level, what is SPC? Well, it's a way to use data. It's a way to use the mathematics of statistics to improve and control systems and processes, and even looking at things like diagnostically figuring out what things are going wrong. So I always say it's about reducing defects, which is kind of output focused. My process is producing something that the customer would not be happy with. That's one part of it, and we want to improve that yield. The other part is improving quality, and there's all kinds of quality principles and process best practices that by using statistical process control, you'll be armed with the information to improve your processes, not just in terms of output, but also in terms of in-process quality. What I like about statistical process control is that it really helps us answer a lot of operational questions that I feel other analytical approaches or data approaches don't quite hit the mark with. So I've got two examples of questions up there. Is a hospital ER capable of seeing patients within 1 hour of arrival? If I was looking at a bar chart and I had the average, wait time, I don't know if I'd be able to answer that question. And I certainly wouldn't understand the tolerances of, how likely that wait time would exceed an hour. Same with, producing defective parts in a manufacturing setting. What's the cost of producing defective parts? How many are we producing? How is that affecting our margins? All of this can really be answered best by statistical process control. And I think that the real thing about all of this is you're getting into the concept of variability. By how much does the product vary? And it's a matter of by how much, not whether or not the product varies or not from unit to unit. So as I'm trying to move my screen here, Aaron, and I'm running into a little bit of an issue. There we go. Thank you. We're going to look briefly at the history of statistical process control. I've got black and white pictures here, so you might think that this is really old, and it is. It's about 100 years old, but in terms of engineering and mathematics, this is really new stuff. This is actually kind of cutting edge stuff when you think about how old the disciplines of math and engineering are. We're just getting to this, in the past century. So there's this guy, Walter Shewhart. He's working at Bell Labs in the 1920s, and he's looking at transmission reliability of telephones. And he's really identifying, using control charts, using statistics, the very first person to really do this, two different causes of transmission reliability variation. We'll talk a little bit about them later on. We'll talk a lot about them later on. But really, he identifies these as common cause variation and special cause variation. A little thing called World War II happens, and then after World War II, we have two kind of eminent figures in the quality management space. The first guy is W. Edwards Deming. If you've ever heard of total quality management, he's essentially built it. And essentially, he was a consultant for the US government. He went over and helped rebuild the Japanese economy, and he put all these principles of quality and statistics and process control that really helped build the Japanese economy back after the war. Another eminent figure was Taiichi Ohno. He created the Toyota production system. If you've ever heard of Lean, this is pretty much the guy who's originated it within Toyota Motor Company, of course. And then finally, it's not really until 1986 that a company called Motorola creates Six Sigma. So if you ever heard of Lean Six Sigma or Six Sigma, essentially this is a problem-solving program that Motorola develops to help reduce variation in their processes. What they were facing at the time is they had too many defects, not a lot, but one defect per 100, one defect per 1,000. But their products, their telephones, had several thousand components in there. So they because their defects were so high in terms of 1 out of 100 or 1 out of 1,000, they never really could put together a reliable product. So by decreasing the variation and using statistics and some of the stuff we'll talk about, they were able to reduce that variation, improve their final product quality. So that's kind of a brief 100-year timeline of statistical process control.
Very good. Let's give you a try again, Michael, if you click on the screen and see if you can take back control real quick. If not, I'll keep us going.
I'm running into issues here, Aaron.
No worries. Let's keep rolling.
All right. And I'll just call out slide when we need to. So what I have here is going back to a couple slides where I said, variability is everywhere. Your product will certainly vary. And here I went to the local Kroger or the local supermarket, and I went to the distilled water jugs. And you can see here just how much variability is in their final products. So the one on the left, you can see the water level is far too low for what a customer might expect from a full gallon of water. It's probably not even a full gallon. Likewise, in the center, you can see that it's way too high. There's probably spillage at the bottling assembly plant. If the customer opens that tab, they're probably going to spill water all over the place. And then you have kind of maybe where the Goldilocks third picture here of maybe that's where the water should be. But nevertheless, we see that there's variation occurring all over this process. And Aaron, if you go to the next slide, please. Some other fun things that I've taken pictures of. I've got some string cheese that I took a picture of a couple years ago, and essentially you can see the difference in volume of, hey, this string cheese right next to another one is like twice as big. It's longer, it's thicker, and you can really start to think about the cost associated with not controlling variability. They have less margin on this piece of string cheese than the other. And you start to wonder, at what point is this wrapper not even going to be able to seal properly because this piece of cheese is too long for the packaging that it's supposed to be in. So again, they're not controlling variability. And even here on the right, you can see I've got these cheese turtles, and they're kind of embossed with this turtle feature to them. And you can see the two in the upper right corner, they're like over embossed, like something happened where, it's not perfect. And then the one in the bottom left, it wasn't embossed enough. So it's not to say I'm not going to eat these, but at some point, if all 24 of these turtles look bad or they don't look like turtles, it is going to dissatisfy the customer. And it is going to be what we would call a defect. So if we jump over to the next slide.
I think you've got it now. That was my fault, Michael. Try one more time. I bet you're going to get this. Now click, and it's all yours, sir. There you go.
All right. We're rocking and rolling. Now, compare those cheese turtles to some Tylenol I took pictures of. You can see that the variation is far, far less, right? Every one of these tablets of Tylenol have what I assume is a laser etched insignia of what the drug actually is. And this is to show that when you are controlling for variability, you can get these tolerances much tighter, and you can reduce the amount of defects you're producing. Obviously, the system is different. Obviously, the capability between embossing cheese crackers and Tylenol, you've got different systems in place. But even comparing Q-tips against each other, you can see that there is variation. There's different sizes in the stem of the Q-tip. There's different widths in the cotton swabs. But generally speaking, there's a tight tolerance. There's not great variability like we saw with the water jugs or what we saw with the cheese sticks. So variability is everywhere, but by controlling variability, we can create a more consistent product, which is actually going to help us out and delight the customer a whole lot better. So that's kind of what I do at cocktail parties, looking around for things to compare and start great conversation. Where this takes us is a question of mathematics and a question of statistics. The basis for everything we do in statistical process control is more or less the bell curve. So if, a quick refresher of the bell curve is it's symmetrical. It's very important that it's symmetrical. So the mean is equal to the median is equal to the mode. And then half of all of my population is going to fall below my mean, and half of my population is going to fall above my mean. So, if you think about test scores, some part of the population is going to score above the average, maybe in the A range. Most of the population is going to score in the B range, and then some of the population is going to score below a B range. So that's very important, and we can actually quantify this. Have I lost it again, Aaron? Oh, there we go. Perfect. So we can actually quantify this in terms of what percentage of the population will actually fall into different parts of this distribution. So, what's the probability that a data point picked at random falls within one standard deviation of the mean? Well, it's about 67, 68%. What's the probability that a data point picked at random falls between two standard deviations? Well, it's about 95%, and so on and so on. So the further you get out, the more standard deviations you capture. Just to recall, what is a standard deviation? Well, it's really a measure of dispersion for a distribution. So again, if you look at the blue, that's kind of like our normal distribution, our regular distribution. A less dispersed one, perhaps we don't have as many A's, as many A pluses as the orange distribution, but there's less spread. We also don't have as many low grades. They're kind of all hovering around that B, average grade. So standard deviation here is just a measure of dispersion that we try to capture. The greater the standard deviation, the more dispersed my distribution is. And that's very important when we talk about statistical process control. So as we move over to the next slide, the first thing we wanted to talk about with that in mind is process capability. So again, I've got my water jug example over here on the left. We're going to create some kind of customer tolerance that says, you know what, above this watermark, it's too high. Below this watermark, it's too low. And I've got a target. I've got my Goldilocks average that I'm aiming for. So we can start thinking of process capability as how capable is my process of meeting these customer specifications. And you can see that the more variability I have, all things being equal, I'm going to have some of my water showing up too high above the customer specification and some of it being too low. And as I tighten that distribution, as I make the variability less and less, more of my population, more of my water jugs are going to fall within the customer specifications, which means I'm producing less defects and I'm selling more water jugs, and they're not spilling all over the bottling assembly plant. So a really important concept that in order to increase process capability, we want to reduce variability. Ways of measuring process capability are several. I think the most straightforward one is this last point here, the yield percentage. So that's really looking at how many good were produced. So let's say I had 90 water jugs that were within spec and I produced a total of 100, I would have a yield of 90%. Looking at that slightly differently from an output perspective, we could say, well, how many defects were created? I had 1 million water jugs and I created 500 defects of them. Well, I have a defects per million opportunities of 500. Somewhat differently, not necessarily looking at the outputs, but looking at the distribution, the population distribution itself, we can say, well, what's the sigma level? How many standard deviations fall within the limits of my customer specifications? And again, the tighter, the more narrow that distribution is, the more standard deviations it's going to take that's going to be captured within the customer specification limit. This is actually where Motorola got the idea of 6 Sigma, right? They wanted 6 standard deviations to exist between each customer specification limit, which is really, it's about like 6 defects per million opportunities. So really small number of defects, very small part of the population actually creating a defect. Everything else is within spec. I'll give you an example of how I've seen process capability used and how I've used it in my own career. I worked at a tire production company. I worked in a manufacturing plant, and essentially what you see here on the right is what a tire looks like before it's cured. So it's raw rubber, it's sticky to the touch, it's shiny, it's kind of a cool material, but then it goes into this curing press, steam and pressure turn it into the tire that we know and love today. We were facing an issue with this though, because essentially when the air has to escape from the tire, we have these little vents. And if you've ever seen these like kind of rubber stems on your tires, that's what it was. It was this vent that that air escaped out of the tire. And if these vents get too big right here, particularly on what they call the bead, here we've got one 7 millimeters, another one's 12 millimeters, is that sometimes these vents will wrap around, it won't let the tire seal properly on the wheel, and you'll have a very slow air leak. And in this particular manufacturer, unfortunately, this happened at the North American Auto Show in Detroit. So it was really visible, and it elevated the issue because you don't want to go to the auto show and your tires can't hold air. As a tire manufacturer, that's not great coverage. So we did our own capability analysis. You can see here I have my lower spec limit at 0, I have my upper spec limit at 5, and our distribution of the data we looked at, we had 434 tires we looked at. You can see that we weren't capable of meeting the customer specifications. In fact, we were like really far over, and we had a lot of outliers, and we weren't centered on the specifications either. So this alerted us to that this is a systems process or a systems problem, right? There's something going on that our process is just simply not capable of meeting the customer specifications. We could only know this through process capability analysis. And we'll get into it a little bit later on how we can actually improve this and take corrective actions to improve the process. Another fun example that I had is I worked at a pizza company, and I'm in the southeastern Michigan right now. We have 2 pizza companies that are multinational in southeastern Michigan, so you can guess which one I was at. But we thought we were going to be really smart, and we actually were doing contracts with a pepperoni vendor. And we said, look, there's going to be some variability in their process, so we'll give them 13 slices plus or minus 2 slices. We thought we were so clever because, you know, that way it controls for variability and we can create a more robust contract. It kind of protects our company. What we didn't expect was that the vendor knew a thing or two about process capability as well. And they actually had greater process capability. They had less variation than a contract of plus or minus 2. Their variation was closer to like plus or minus 1 slices in a package of 13, which means that they sold us a pack of 12 pepperonis and we paid for a pack of 13 pepperonis every single time, which in a multinational pizza company, that adds up very quickly. So I think it's a really cool example where you can see not just how process capability can be used to protect yourselves, build quality, reduce costs, but how if you really know what you're doing, you can go on the offensive and you can, you know, get into agreements like this where you can really, you know, eat the lunch of somebody, if you will. So a really cool example. I still remember it to this day, even if it kind of beat me up a little bit. So that's process capability. That's one tool that's really helpful in statistical process control. The next thing we want to look at is control charts. And here I'm using the water jug example again. And now instead of looking at like this distribution of maybe like 1,000 water jugs or whatever, now we're looking at individual observations kind of on a timeline. Observation 1, observation 2, et cetera, et cetera. Now the difference here is that these are no longer like spec limits, like, oh, the customer doesn't want it this high or this low. Instead, what these are is they're essentially measures of standard deviations. How far away from the mean in terms of standard deviations are we willing to say this something's going on here? Something is very different. And if you remember that normal distribution that I showed just a couple slides ago, where we showed, 34% are within within one standard deviation, 95% are within 2 standard deviations. Essentially what that means is if I'm 2 standard deviations away, 5% of the time, this little point out here is going to be part of my normal distribution. The other 90% of the times, it better fall within this range here, which also means that essentially we're creating this hypothesis that says, if this data point falls outside of our spec limits, essentially we're saying dollars to donuts, that's caused by something other than the normal operation of our process. And that's kind of what's going on in control charts, is we're taking that, we're making that risk and say, you know what, 5% of the time it's going to be a false positive, but the other 95% of the time it's going to be something we want to investigate. And we call this special cause variation. So we have 2 types of variation now. We have common cause, which is what we just looked at in process capability. My process is going to vary. Sometimes it's going to be above the mean, sometimes it's going to be below the mean. But in some occasions, when it's beyond this threshold that we're calculating using, pretty robust statistics, we can say, you know what, that we might be tracking down a ghost 5% of the time, but chances are if that thing comes either above our upper specification limit or below our lower specification limit, we're going to identify that as something influencing, something external that's influencing our process. So that's, again, that's that Shewhart principle from the 1920s, where he kind of invented this to trace reliability issues in phone transmissions. So, phone transmission varies based on wind and maybe temperature, but if a tree falls on that transmission line, that's going to create a really special cause variation. And that's what he was trying to identify. Because by discriminating between these two, we can take different problem-solving approaches and actions to improve our process. So again, just one more example here. It's the same data as we've seen. The variation of these blue dots are within our spec limits. We really don't have to do anything about this. We shouldn't be concerned really about the variation we're seeing here. But if something is exceeding one of these thresholds, we should raise our eyebrows at it. We should say something's going on there. There's a smoking gun that made that data point do what it did. And that's reason to investigate further. So some other uses for control charts, in addition to what we've already looked at, is you can look at the weight per unit, which is kind of a measure of defects. In the tire, in the world of tires, you might have too much rubber. They might fluctuate, but you could also start looking at, did I miss a component of my tire? Is it significantly below the weight that it should be at? And then we can start to create signals to catch tires that were not created correctly. Likewise, we can look at time between batches. Again, this is pizza dough operation. So if there's a long wait time, we can start to assign causality to that, as well as defects, kind of the yield that we talked about earlier, and then also controlling for cold chain temperature in kind of the distribution and supply chain of food. We can start measuring in real time or taking samples to say, hey, we got to make sure that the dough, in this case of the pizza place, the dough is remaining within temperature. We have a process that's capable of transmitting this dough from the dough production facility to the different pizza chains, still within temperature, still within what's safe to consume. So all other examples of using control charts. And Aaron, I'll turn it to you.
Yeah, so this is kind of a softball question. I'll admit that up front, everyone. But we did want to get your take your pulse again and just ask a very simple question. So we're going to do another poll. So look on your screen really quick. It's going to pop up, and it's just your opinion, right? What are, in your opinion, the best uses of SPC? Michael pulled us through a lot of different examples: the water jug, like the crackers, right? The cheese, or the cheese sticks. But when you look at how much you can accomplish with just SPC, statistical process control, where do you see the most value? And you can pick one or more of the following, right? Oh no, I guess no, we didn't do that one. So it should just be, you got to pick one. So in any case, what's the best one, right? What's the best use of SPC? Control costs, right? That's huge. Improve productivity and yield, improve uniformity, and reduce that customer complaint. Michael, you're saying if somebody opened up that water jug when it was too high and it splashes out, that's a negative brand effect. That person is going to remember that, wow, that shouldn't happen. Are you looking to say, hey, I need to see shift, line, batch, lot, and maybe even facility trend reporting, that enterprise capability, right? Or nothing. SPC is a waste of time. So let's close this poll. Looks like nobody took the bait on that last one, but I'm going to share the results really quick and then we'll go on. So anything, this is a pretty good, I think, representation of really what people are using this for. In your line of work, is this kind of, when you're consulting, Michael, is this what you're seeing mostly too?
When I consult, they're usually bringing me in to do one of the first two, right? Is I've kind of got to pay for myself and then some. So usually it's a lot more of productivity and yield. I'm happy to see that 50% liked uniformity, liked reducing customer complaints. Uniformity is a great measure in the tire world of, do you actually have a round tire? And is it, there's levels of tolerance there that the customers will not tolerate. I didn't mention, and I kind of wanted to, and I forgot about it, this trend reporting. Control charts are a really great way to look at trends in your data, not just to say, am I signaling anything, but am I trending upward? Is my operation moving one way or the other, and is this good or bad? So I think there's a lot of opportunity there, and it's insightful for the 5% who picked that as well.
Yeah. Well, let me hide these results. And I wanted to share. So I noticed something. I eyeballed it, and you tell me if I'm wrong. I'm probably wrong because I'm often wrong, Michael. This almost looks on the right side like you're about to hit a run rule. The last 1, 2, 3, 4, 5, 6, 7, 8 observations. You're almost going to hit a run rule, and that's a really interesting part too. I love the special cause and common cause. This is new to me, so I really appreciate you walking us through this. But in any case, all of these are valid uses for sure for SPC. So let's get back to crackers.
Yeah, thank you. I'm not gonna get into all those rules, like the run rules, but essentially what Aaron is referring to is that there are different types of signals that we can look at, not just special cause or common cause, but if we get more into the statistics of normal distributions, what's the probability that something at random falls on one side of the average 8 times in a row? Well, it's the same as flipping a coin 8 times in a row and getting heads. And again, it's not to say that it could never happen, but it's to say that at some point something's going on. We're gonna take the guess that, hey, something's moving our process towards one side of the average versus the other, and that can signal us that there's something going on in the process that's worth investigating because the process is changing and in a unique and sustainable way. So thank you for that, Aaron, and that's a fun little signal to look at. But nevertheless, one of the things that we look at a lot in terms of quality is just pass fail. And this is not necessarily the best way to look at quality. One, because it's output driven, it's not process driven. We've already produced a product, and now we're essentially saying whether it's fit for the customer or not. And we've already put all of that process work, all of that value into it, and now we're rejecting it. So that's one issue with it. But the other is that it doesn't produce very good data for us. So when we use statistical process control, we kind of have to have this what we call scale ratio data. Essentially, it has to be a measure of something. And when we have pass fail, we actually have something called binary data. It's just either yes or no. And what we do a lot of times to create statistical process control in this is we parse the data and create proportions. So here I've got my 24 cheese turtles. I take the 3 defects that I found and I create a proportion of defects. In this case, 1/8 of my turtles, 3 of 24 is 1/8 were defective. And now using this kind of ratio scale data, I'm able to create a meaningful control chart in a way that I wouldn't otherwise be able to do just looking at pass fail data. So another thing that I like about the control charts is that because you're using statistical process control, and because you're using the standard deviation to set your control limits, to set kind of your signal limits, as you change the subgroups in kind of these what we call P-chart proportion charts, we see that we can actually get tighter tolerances. The more subgroups we take, essentially the more data we have, the more sensitive we can become. This is like a tenet of statistics, right? It's like I'm more confident after surveying 100 people than I am in surveying 3 people, right? I've got a better sample that's going to be more representative of the population, and I can take more liberties in my sensitivity because of that. And that's kind of what we see here with my turtle chart, is that I had a subgroup of 90 versus all the other ones I had 24, and my limits got much tighter. I'm going to be more sensitive to changes within this subgroup. So just something to note, it's kind of a tenet of statistics as we look at that. And now a couple things that I like to go on tangents with is I use Excel extensively, and I'm stupidly good at Excel, but one of the things I don't really care for is actually creating control charts. They're very helpful and they're very useful in explaining what's going on and what we're looking for in terms of signals, but they're actually very difficult to update. So here I would have to click on the chart, I would have to come over here, I would have to drag down the data to repopulate the chart, and sometimes formatting goes crazy with that as well. They can also become quite difficult to read. If I had to ask real quickly, how many signals do you all see, I would probably get a distribution of answers, and it'd be very difficult for me to say, it was observation 6, it was observation 23. It's just the traceability of it is very difficult. It's helpful with a visual management perspective, but it's actually quite difficult to summarize and aggregate. So one solution that you can come up with that I use quite a bit is what I call control charting without charts, where it's essentially whatever signal you want to create, whether it's that run signal that Aaron was talking about, or the special cause and common cause variation that we were looking at, we can look at if our response, in this case that proportion, is above the upper specification limit or below the lower specification limit. And in this case, we see that it was below it, and therefore we get a signal that we just code in as low. It's just a simple logic, right? If this column is less than this column, low, else if this column is greater than this column, high. And that's what we did here, and we see it down here. And the other great part about this is now I can do very simple formulas within Excel to capture these aggregate data. How many high signals did I have? Count if equals high. There you go, I can figure it out with just a couple very straightforward formulas within Excel. So something else just that I really like. So that's kind of the signals that I wanted to cover today. We have special cause and common cause. Now it's kind of like, what do you do with a special cause? Okay, you identified that sometimes something is affecting the process. Okay, what do you do about it? And one of the things that we do in the Six Sigma world, the process improvement world, is we do something called root cause analysis. So when looking at root cause analysis, I've got 2 tools that I use quite a bit. The first one's very straightforward, and you can learn it right here, right now. It's called the 5 why. And essentially you start with the problem and you work backwards, just asking why 5 times to get to the root cause. I won't go through all of them here, but essentially I had a water bill that was higher than normal because I've got a lot of free time on my hand and I make control charts for my utilities. And essentially I was able to do a 5 why analysis to find that I had a small leak, and the reason I had a small leak was that a rubber gasket was old and it was cracked and it had worn away. So my countermeasures for this is not simply just to replace the rubber gasket, but it's also to set up kind of a more robust plan to inspect all the gaskets that I have in the house, to buy the correct size spare gasket, so if something does go wrong, I have it available for me, and also set up a PM plan, either lubing it up with Vaseline or something to keep the gaskets nice and wet still. So just an example of how you can use the 5 why, starting with the symptom. That first thing that's going to be your pain point is always going to be a symptom, but it's very rarely going to be the root cause, and the 5Y gets you that root cause. The other tool that I use quite a bit is what I call fault tree analysis, and essentially what you do is you just figure out kind of that next step. Okay, I took a cold shower because the water wasn't coming up. Why was it? Well, it could have been an issue with the water supply, or it could have been an issue with the water heater. And let's say it was the issue with the water heater. Well, it could have either been a heating element or a water tank, and so on and so forth. You can take this down further and further and further, and you can see that there are all kinds of reasons that my water tank that would be defective, that would create my cold shower. And in this case, what I actually found was that the pilot light was out, and the pilot light was out was because there was a pressure imbalance in my basement. So now my solution is not to, take cold showers or whatever, buy a new water tank. That's not going to fix the problem. Instead, fixing the pressure imbalance is the correct solution, correct countermeasure for the root cause that we found. So 2 examples of root cause analysis and kind of why they're useful in special cause variation. Now, we use root cause analysis and special cause variation because there's a smoking gun, right? We know that there's something external that's knocking our process off its bearing. What do we do when it's just common cause, when we just have a system that's not capable of meeting customer demand? Well, we can do one of 2 things. The first thing that we can do is we can shift the mean of our process. That's if the data is not centered on our customer specifications. We simply shift the mean, we get it within our specifications. Here, let's say we have a talent acquisition process. It averages 60 days plus or minus 30 days. And in changing our system and changing the process, maybe we go with a new background check vendor and they get back to us quicker. We're able to decrease the average time it takes. The variation is still the same. We haven't done anything to the variation, but we've just shifted that mean. We've essentially centered it on our customer specifications. And again, there's no smoking gun here. There's not what went wrong. It's no, this is what our process is capable of. We can't look for that smoking gun. The second system improvement is decreasing variation itself. So again, we have the same process. It's 60 days plus or minus 30 days, but now the improvement is not to shift the mean. You can see the mean is still 60 days, but the variation between data is much, much tighter. So this is another way to improve the process, is through decreasing variation. So 2 ways: shifting the mean and decreasing variation. This is going back to that tire example of when we saw that we were way out of spec for what the bead vent length needed to be. We identified that as a system-based issue. We couldn't find a smoking gun, so we went with a system-based solution. We brought in new tooling, which was going to change the current state of the process. We were able to shift the mean from like 5.5 down to 0, and we decreased variation as well, because all of these vents pretty much don't exist anymore. So that was how we used the principles of solving systems-based problems using systems-based solutions, and we weren't looking for a smoking gun that didn't exist. So when you're talking about prioritizing system solutions, kind of what target is easiest to get to the desired state. So if I want target D, what's the easiest target to start off with? And when you think about what's going on here, essentially you're pretty accurate, but your grouping's not great. And over here, you've got a great grouping, but you're just not accurate. And generally speaking, it's far easier to decrease variation and then shift the mean. Here, if I've got a really good grouping and I'm shooting at this target, all I really have to do is adjust my sights. And now that my sights are adjusted, I'm going to hit the bullseye every time. Versus here, it's like, okay, I'm shooting at it right, but I've just got a lot of variability. I need to control my breathing. I need to, do this, that, and the other, change my positioning. It might be more difficult. Particularly true in processes as well. Always try to improve variation first, because you're going to have a better understanding and control of your process, and then you'll be able to shift it to the desired state. So that's in a nutshell what we talked about in statistical process control. It's effective for understanding and quantifying the current process. I also think it's really, really helpful from a diagnostic tool as well to figure out what's going wrong and what I can do to improve it. Process control charts are particularly useful to understand changes over time. That was that trend I was talking about just briefly as the poll question kind of alluded to. And in particular, I think common cause and special cause variation require different approaches to actually improve the system. And knowing that and discriminating between those two is really the first step, I think, in combining statistical process control with continuous improvement.
Fantastic. This is great. We've got a couple of questions coming in. I'm going to just remind everyone, if you have some questions for us, put them into the webinar console under the questions. And this is great. I love the common sense approach that you took to this, Michael. This is a really easy to understand sort of way to look at SPC and how it can really help any kind of manufacturing, right? Really appreciate that you pulled some pictures in from your career and kind of looked at some things that you've done. Really neat though, this is the first time I've seen anyone put together SPC and root cause analysis like that and use a couple of the methods to doing that, the 5 whys and so forth. So very good, love it. I'm going to get to the screen though with your information so that we can make sure people have some time to check this out, because if you do have some more questions, sixsigmaconsulting.com is where you can kind of peep out where Michael Parent is. He's on Twitter and LinkedIn. Please get the book. I'm going to probably go get a couple for our office here in Novato. Thank you, Michael. And then let's just get to some questions really quick. So Leah asked a really great one, and I'm going to be super biased, Leah. Or Leah, pardon me if I pronounced your name. What software do you recommend to do the charts? Well, SafetyChain does this really well. So, listen, if you are looking at software recommendations, I'm going to take a staunch approach. Do some research, look at some options, do your vendor demos, and see what works, right? Because there is going to definitely be some differences depending on probably what you're manufacturing, that some software providers can do better, and but SafetyChain can certainly do all of those. So got another question for you here. This one's yours, Michael. How do you go about developing controls, targets, like the targets from the start, right? Like how do you develop, if you got nothing and maybe it's a new product development or something like that, where do you start?
Yeah, if it's new product development, and this gets a little bit into human-centered design, it's very, very important to have the voice of the customer in there. So I know what the question is, and I would say, yeah, try as best you can to say, look, I need to figure out what the customer's tolerances are.
Yeah.
Even if it's the absolute tolerance, I think it's better to start wider and then find out, oh no, they actually didn't like that. It needs to be a tighter tolerance. I think that's very helpful. And then I would also say, just kind of as a general rule, if you really don't know, and maybe you're doing this yourself, you're trying to kind of do a grassroots thing, I would say 2.5 standard deviations is just a good kind of solid number for your control charts. Most processes are not Six Sigma level processes, so you'll not see too much false positives, but essentially I think 2.5 standard deviations is a fair value in creating those control limits for control charts.
Yep, good. This one goes back to the cheese picture. They posted this up. Josh says, how do you know, or how do you find, sorry, this is written oddly, but how do you know or find why that cheese was so variable, right? And we kind of went through some of the methods, but if you just looked at that cheese, a lot of different things could be happening in that process, right? You mentioned a couple. Cheese needs to be heated up into a specific location, and then it cools, right, to be able to fit the packaging. There's so many different ways to find that variability. Do you have any advice, Michael, on how to start that sort of process of understanding what that variability is? Like, is there a preferred method you use or anything like that?
Yeah, I think the first thing you have to figure out is this a special cause or is this a common cause? Now, I'm not that special, and I sincerely doubt that I got that lucky that I found some kind of like one-off special cause variation in my string cheese. So I would bet that that's actually something that's system based, right? Is there's no smoking gun there, which means the process is not capable of producing cheese. Not it's going to have a lot of variability built into the process. So that's the first thing, is let's figure out that it's a systems based issue. Now that it's a systems-based issue, we go in the lean world, we would call this go to the Gemba, go to where the work is done, and we need to observe what's going on. We need to, essentially work from the product, like at the end of the process, and work backward through the process and really start to understand where the defects occur, where they could occur, and really just understanding your process, but working through it and understanding that output is not surprising, right? Something is happening that's creating that output, and we can go in and assign what that is. And maybe we have to, buy new machinery to make it more capable. Maybe we need to have better quality checks at different points in the process. Cheese is weird, but you can think about even in manufacturing, a lot of folks would have a lot of quality checks in the raw materials before they even enter the plant, because they know if they don't get the right stuff at the very beginning of the process, they'll never get the right stuff coming out of the process. And I think the same is true for string cheese.
Yeah, yeah, and I think especially in the picture that you took, I believe that was round edge string cheese. So like there's a difference between those blocked ones. So if you're chopping, if you actually have a slicing machine, then that could be it. But that wasn't the case. That had round. So
Right.
humidity and heat have a lot to do with how well that cheese kind of comes into the form. So there's a lot of different things. And what you'll know is that you got to just start. I liked how you said the Gemba. I've never really thought, I always thought of it like, hey, just go look, go and observe. But I never thought to go, oh, you start at the end and then work your way back. So that's fantastic. Thanks for
Yeah.
that.
And one other thing, Aaron, we can talk about this later, but you talked about heat and humidity. You can do things like design of experiment. If you're looking for a tool, search design of experiment 6 Sigma or something, and you'll see that there's just robust, really, really cool, high-powered statistics where you can really figure out exactly, what your main effects are of your process, what things are really affecting, and what things might be interacting with other things in your process.
That's awesome. I think we're going to definitely be able to geek out on some of that stuff later,
I hope
Michael.
so.
I can tell you we're cut from the same cloth. So got another one. Robert asks, how can control charts help my first pass yields? Love it. It's a softball. Take it away, Michael.
Yeah, so control charts helping your first pass yield. He's getting at a really important concept here of right the first time quality, right? This is something that we would look at, is not just yield through the system, but getting it right the first time. So obviously I would say is figure out what your tolerances are, right? Why are you, is your yield higher than what you would like it to be? You can start to do some root cause analysis to figure out what these special causes are, but you could even, with your control charts, start to compartmentalize the different reasons that it's failing that final quality check. Are there different defects? Is it all the same defects? We could talk a little bit about Pareto charts and creating charting based on kind of the causes for defects. And then from there, you can kind of prioritize what you want to attack. And again, I would say attack it first as a root cause analysis, or excuse me, yeah, first as a special cause, root cause analysis, get rid of all the special causes, and then start working on the process mainly through reducing variation.
Yeah, I love it. And I think what we've found, especially with our customer base, Michael, more often than not, Robert, what we find is it takes a while to understand the processes and understand the data to get to the part where you are controlling and helping to improve first pass yield. But what ends up happening is we've learned, oh wait, our upper and lower control limits are a little wide, or our process is in very much control, but it's too high. Like there's always this room, it seems like, for being able to reduce the overfill. Or in some cases, if you're cooking, right? If you cook the margin out of the weight of your if you sell on package weight, you may be cooking it too long and thereby reducing the overall weight. There's a lot of ways. This is the method to find it, though. That's the important part to take away from this, Robert, is once you start doing these charting, you will find maybe not the golden or the smoking gun like Michael was talking about, but you will over time develop firmer processes that are in tighter control and lead to that spec that you really want to get. Next question is one that I've always had a question about, and I don't know if it's an opinion-based question, but Michael, what makes a minimum statistically valid sample size?
That's a good question. The rule of thumb, if I went to my my textbook, I'd say 30. What you're really looking at is something called the central limit theorem, which says essentially regression to the mean, right? Is the more samples we have, the more likely that they're going to turn normal. And I think a good rule of thumb is 30. But there's definitely like different calculators out there. It's not something I'm particularly well versed in. I'm not a statistician by training. I'm an engineer. But I think there's a good number of calculators that you could find on Google to find that. But as a rule of thumb, 30 I would say is good, and I would say more is better.
Exactly. And I was going to say that last part you just said is what every statistician says. The more, the better. But what you do is if you get lower amounts, what you find then is your confidence level, which is an actual number, gets lower because it's not able to predict the accuracy as well of that sample size. So.
And I think you're right. I think if you look at some of those calculators online, one of the parameters that they'll put in to those calculators is, well, what does my tolerance have to be? Which is essentially kind of reverse engineering the question, right? Is, well, if my confidence level has to be between these 2 points, then I can say that and I know the standard deviation. That's the other piece, right? Is you need to know the confidence level, the mean, and the standard deviation to figure out what your sample size needs to be.
Yep, and we got one last question, and I'm coming back to where they saw it. So Jill asks, what is can you explain that Excel formula? So it's just an Excel formula, but what you're doing is you're going to drop this data, the count of high, over on another column, right? Is that the case here?
Yeah, so let's say you're have a dashboard, or somebody asks you offhand, hey, how many high signals did you have in that control chart? And my point first in saying is that it's nearly impossible to get a really good answer with looking at the chart. You kind of need something that's in a column form that is, saying high, saying low. Essentially, this is kind of this is not actually the correct formula in Excel. What you would need to do is say equals count if, open parentheses, then select the range that you're looking at. In this case, we could select all of the signal column, and then you would hit a comma, and then you would say, high in those quotations. And then what that would do is it would return how many cells within this range, within the signal column, contain the word high. And that would tell you how many high signals you actually had. So there's a little bit of conditional logic in there in terms of counting if, which itself is based on the conditionals of looking at the p-value versus the upper spec limit and the lower spec limit.
Yep. Okay, great. Thank you. Appreciate that. All right, well, let's wrap this up. Kevin, I appreciate this. This is fantastic. Couple of things coming up. Lots more resources at safetychain.com. We are going to be talking about accessibility in food safety training with Lily Yang from the Atchison Group next Friday. Fantastic. I think this is a very, very very interesting discussion point to have, especially to create a diverse workforce. What does that take? There's going to be a great, and Dr. Lily Yang will be with us next week. Got a bunch of other stuff, white paper, surveys, webinars, videos. If you do want to get a demo of SafetyChain, go grab one, right? We're happy to show you what we've got. There are definitely ways to automate some of these things and make your life easier. So with that, Michael, this has been great. I think we're going to be reaching out to you again, maybe to do another maybe deeper dive on this. We've got some really good questions here. Really a pleasure having you on Beyond Compliance. Thanks again.
Yeah, thank you, Aaron. And thanks
All right.
everybody for listening.
And that'll wrap it up for us for Beyond Compliance, everyone. I appreciate your time. Have a great day. That'll end the webinar.